Good morning. My name is Stuart Halloway. We're going to talk about the Clojure programming language, simple by design. I'm going to start by saying a little bit about Clojure, the little language that could. Clojure has risen from not existing a decade ago to being a language that actually got promoted off the Thoughtworks Radar. So Thoughtworks is a global IT consultancy that, among other things, puts out this radar that tracks how organizations are and or should be considering adopting things. Clojure got moved into adopt in October 2012, and actually an interesting characteristic of the Thoughtworks Radar is after something gets adopted, they just assume it's such common practice among developers that it actually gets promoted off entirely. So now there are people who are coming to look at the Thoughtworks Radar to see where Clojure is on it, and they're like, oh, it must not exist at all. And actually it's gone out the other side. Clojure is also in the Redmonk top 20. These are both what I would call leading edge indicators of programming language popularity. These are what people who are doing greenfield projects and people who are in skunkworks teams in Fortune 500 companies are able to do. And these are indicators that in the fullness of time will be followed up by more mainstream indicators like job trends and so on. We're going to talk about three things really: Clojure, simplicity, and design. And so I'm going to start by defining terms. Design is a specification of an artifact using components to meet goals subject to constraints. And you will see a lot of software work that does some of these things but not all. One of the most common fallacies I think you'll find is goal-directed thinking without constraint being brought in. So you'll see things being touted only in terms of their benefits. Right? I have this goal and this thing is good, X, Y, Z. It also has problems and constraints, A, B, C, D, E, and F, but sometimes those get left by the wayside. I'm also going to define simple. Simple actually has a remarkably brief definition. Something that is simple is not compound. That's pretty easy, but it's actually the historical definition of the word simple. It's not how the word simple often gets used, and so it's important to talk about a lot of characteristics that software, or in fact any design system might have, that are valuable but not really related to being simple. Something could be convenient. Convenience is great, right? I want things that I use to be convenient. Something could be beginner-friendly. I like that too, and you see a lot of that in the open source world, right? I spent many years as a Ruby programmer, and it was a very warm, embracing community in general, and specifically very embracing of getting started, right? It was a really fantastic environment, so that's valuable. Something can be easy. Easy is a tricky thing, of course, because easy is relative, right? If my name is LeBron James, dunking is easy. But for most of us, dunking is hard. So easy is a relative thing. It's not an objective measure of quality. It's a subjective measure of quality relative to you. Something can be familiar. Familiarity is a valuable thing because it means that I'm going to be able, if something is familiar to a lot of people, I'm assuming that I can go into a room and talk about it, and they're going to know what I'm saying. Or if I'm trying to build something, I can say, hey, let's do it this way, and I can use words, and everybody will understand those words. A lot of times, people use the word simple just to mean small. Right? So if I have something that has 10 steps, and then I give you something that solves the same problem in 4 steps, and I said, which thing is simpler? You might say, oh, the thing that solves the problem in 4 steps is simpler. I'm going to encourage you not to think that way. Likewise with count, right? Really size and count. These ideas of simplicity are really dangerous when you're designing software because they get you away from the definition of simple, which is not compound. Right? How can I take a 10-step process and make it into a 4-step process? I compound the steps. Right? I take the steps and I compound them together. So often, a little bit surprisingly to people who are just used to sort of using the word simple casually to mean easy, when you make something simpler, you end up with lots of parts on the floor. You end up starting with something that has 2 ideas in it and discovering that it actually has 10 ideas in it when you break it down. So to make that concrete, I'm going to give you, and this is the plan, I'm going to give you some examples of simplicity in Clojure. I'm going to give 3 examples. Clojure's syntax, a thing in Clojure called protocols, and another pair of things in Clojure called values and references. So we're going to look at those, and then we're going to talk about why. So this is going to be simple. There's going to be more parts on the floor. I'm going to take ideas that you may be used to, and I'm going to explode them into smaller ideas. And then we're going to talk about why you might want to do that, building software. And then, because this talk is about how things get made, not just what's been made, I'm going to talk about how Clojure is built. I'm going to talk about the process of adding to Clojure over time, and how that works and what it's like to run Clojure as an open source project. So let's start with the examples. The first example was Clojure's syntax. This is a nice example. It also has the side benefit that if you never saw Clojure before today, at the end of this example, you'll know how to read Clojure programs. So we all can actually have a vocabulary that we can use going forward. I'm going to start with a Clojure Hello World program. That's what people like to start with in software, seems like. And I'm done. So the Clojure Hello World program is the string Hello World. And the point here is that everything is made out of data. This is another Clojure program which looks suspiciously like an address book record because it also could be interpreted that way. And really there's a small set of pieces, a small set of simple pieces out of which we build things. There are strings inside double quotes. There are integer numbers. There are floating point numbers. These can have suffixes to indicate arbitrary precision. So 42 is a machine precision number and 42n is an arbitrary precision number. There are booleans. There's true, and there's another one I can't remember what it's called, but you probably know. There's nil, and then there are two types that represent names in programs. There's symbols, which look just like programming language symbols, and there are keywords, which look a lot like those, but have keyword colons in front of them. This is interesting, and it's one of the first examples of Clojure being simple in a way that most programming languages you're used to are not. How many symbolic types do most programming languages have? If we went out and surveyed the top 100 programming languages, I would guess that the number of symbolic types that they have, the mean, would be between 0 and 1. Right? Java has 0. Right? Java has 0 types to represent symbols. There's no literal in Java to represent a symbol. Ruby has 1. Clojure is one of the few languages that has 2, and it's a good example of this, taking something that's compounded together, something that serves multiple purposes in another language, and breaking out into a bigger number of things that can be orthogonally composed to make stuff. There are 4 collection types. There are lists. They're inside rounded parens. There are vectors, which are inside square parens, and maps, which are inside squiggly. I can't really make all these. I was never a cheerleader. You can see them up there. They're squiggly parens. Maps are associative. So here we have a map from the keyword A to the value 100, the keyword B to the value 90. And then sets look like maps, but they have the pound sign in front. So that says treat this not as a map, but as a set, so a membership-based collection. Now, the funny thing is, I'm going to tell you one more thing, and then you become Clojure programmers. So if you haven't used Clojure before, hold on, because here it is. There's a rule about Clojure programs. Clojure programs are lists. The first thing in the list is the verb. Everything else is the nouns. I'm done. Right? You now know how to write all programs in Clojure. All you have to do is have an encyclopedia or a dictionary somewhere that tells you what the verbs mean. Right? But you now know all the rules. So here's a program that adds 2 and 2. Right? The first thing in the list is plus, so that's what you want to do. And then the second and third thing are the arguments. Everything works like this. So here's a program that makes new functions. So it's a list, and the first thing in it's a verb. Defin, define a new named function. The first argument to that is the name of the function we're going to create. The second argument is the documentation string. The third argument is the argument defining argument. Things are going to often feel meta when you're building things in Clojure, right? Because it's built out of a lot of small, simple pieces. So the third argument here is the argument defining argument. And the fourth argument is the body of the function. But it's still just data. Right? You could go back to those 2 slides, one of scalars and one of collection types, and say, oh, this is just a list with a symbol, a string, a vector with a symbol, and a list with a symbol and a string, blah, blah, blah. So this is simple. The opposite of simple is actually complex, but rather than sound hoity-toity and use the word, I will be casual and use the word complexity instead. And let's talk about what complexities are avoided by building a language this way. Well, there's not much syntax to learn. I just taught you it. There's not a lot of ordering dependencies. There's not a lot of rules about, if you want to do this, the operator comes in the middle. If you want to do that, it has to come at the top of the file, blah, 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 right? All the ordering rules are laid out in, list, function, argument, argument, argument. There are no operator precedence rules. None, right? There's just first things first. The first thing in the list is applied to the other things. It also eliminates on day 1 a bias for code and against data. Relative to most other programming languages, Clojure is very biased towards data. Other programming languages are variously biased towards code. Java, for example, is extremely biased towards code. It's very hard to write data at all in Java, which is kind of crazy given that it's the dominant language out there, and for a lot of developers, and we manipulate data in our programs. Finally, having a syntax that's simple, that's built out of these small composable parts, eliminates a lot of tedious metaprogramming. Well, how many people do metaprogramming in their first day using a language? Not so many. Right? This tedious metaprogramming thing is something that comes up when you've been building a project for 2 years, and you now want to write a program that transforms your existing program. Or you want to build an IDE that can transform programs. So this is something that starts to be a problem at scale. So that's syntax. Second example we're going to look at is protocols. And I'm going to introduce protocols with a little bit of good old-fashioned object-oriented inheritance. And I'm going to have reversible. That's an idea. There are things that can be reversed. And I'm going to have 3 concrete things that can be reversed. You can have a reversible jacket. You can have a reversible belt. Or you can have a reversible string. Now, I'm going to ask you, put on your object-oriented hat, if that's not the hat you wear all the time. If you wear some other hat most of the time, put on your object-oriented hat for a minute, and tell me what you see here. Map this to actual OO programming terms. And what you see is 2 things, interface and implementation. And those are going to map to certain names of things in your programming language. So in Java, that maps to what? Interface and class. Simplicity is such an easy game. Here's all you have to do. Walk up to a problem and see if there are more concepts than there are names. And if there are more concepts than there are names, it's not simple yet. All you have to do is look at this picture and see that there's a concept without a name. The arrows don't have a name. I'm going to pick a name for it. This is not an industry standard name because people don't talk about it, but I'm going to call that extension. Well, what happens when you have extension? Well, now you have 3 things. You have interfaces, and this is actual Clojure syntax. Notice that again, everything is verb, noun, noun, noun. So an interface definition takes the name of the interface and then descriptions of the methods in the interface. An implementation, here I'm going to create a record that represents a tie that can be reversed. And then I'm going to extend the protocol reversible to the reversible tie that I just made, and I'm going to extend it to java.lang.string. So rather than having 2 things, which is what you'd have in most object-oriented programming languages, you have 3. You have interface, implementation, and extension. Now, this turns out to be a really big deal, because what happens to you if you don't have this? Well, all kinds of problems, right? I want to attach an interface to a class, but I didn't write the interface for the class. What do I have to do? I have to write a new class, and I have to use the adapter pattern, or the wrapper pattern, or the translator pattern, depending on how enterprisey you are. I have to use that pattern. I have to make a new class to represent the same thing as the old class in my system. I now have 2 classes that represent the same thing. Does that feel good? That's not a very good thing. Or if I'm a Ruby programmer, I have to monkey patch. Right? I don't have to cheat at the class level. Instead, I have to cheat in poking around inside. Or my favorite term for this is actually duck punching, if you haven't heard that term before. But I have to do that. Or I have to make up a thing that's about a thing but isn't a thing. So anytime in your program where you have noun utils, you are suffering from your programming language not having carved out these 3 things separately. Now, these problems, they all lead to additional tedious boilerplate code that doesn't help you actually work on whatever problem you're trying to solve. But not only that, they're combinatorial in their impact. Right? What happens when I try to use your code and you try to use my code, and I wrote a class called string utils and you wrote a class called string utils? Now we have string and string utils and string utils some more. What happens when you're a Ruby programmer and you want to monkey patch a class and I want to monkey patch it too? Oh, maybe with 2 we get lucky, right? I don't monkey patch the same methods you do. Maybe now let's compose bigger. Let's say 5 people want to monkey patch that class. What's going to happen? So these complexities in programs matter, and they make programs bigger and more complicated in more subtle ways than just verbose syntax. Right? This isn't just, Java has fat syntax, Ruby has thin syntax. I should use Ruby. This is regardless of what syntax you use. You've got to get the modeling right. The third example that I'm going to give you is values and references. And to do this, I'm going to model something. I'm going to design a very, very small program. And this program is going to model me, because I'm a little self-involved. And it's going to have a very reductionistic model of me. So, I live in Western society in a time where it's really pathetic to have this reductionistic model. But I'm going to be modeled entirely by my weight. Right? That's the sum total of me. Forget about any of my achievements, any of my hopes and aspirations. my wife, my children, my career. I'm just the number, 182 pounds. But then something happens, something really happy. Something really, really happy happens. Nachos happen. Nachos. Nachos. Oh, are you guys still here? Okay, got to keep going. So nachos happen, and then I weigh 184 pounds. That sounds like a lot of nachos. And I like nachos, so that's not improbable that that could in fact happen. Now, I'm going to ask you to model this with object orientation. Well, I must be an instance of a class, right? That's how OO works. So I got that. And then my weight must be a field. But is my weight the field that points to 182, or is it the field that points to 184? Yes. Well, that's a little scary. It seems like I have one idea that's getting stretched now to do two jobs. Nachos is probably a method, but then there's this other question about how this method actually gets applied to the object. Maybe when my weight goes up, the count of nachos in the inventory in the kitchen has to do what? Go down. So maybe there's some business rule that says, yeah, you can add nachos to you, but when you add nachos to you, you have to subtract nachos from somewhere else. But that's not captured in the nachos method. That has to be captured somewhere else with this question mark on the slide. So here's the thing. If you have more things than names, your design is broken. If you can walk up to something and look, I got more things here than I got names for, which I clearly do there. Right? I don't have a name for the idea that this field can change over time. I don't have a name for this, whatever this question mark thing is. I don't even have a name for that at all yet. And what happens when you try to stretch too few concepts to cover your idea is you're using things that are complected. Right? You're using things that are doing more than one thing at a time. And what you're going to find out when you build systems that way after a while is you're going to get to a day where this thing has characteristics A and B. It's red and it's made of steel. And you want something that's green and made of steel. Or you want something that's red and made of concrete. It's like, nope, can't have that. Right? And that's what object-oriented programming does to you. So let me not put too fine a point on it. There's a thing that has more things than names all the time. It's called object-oriented programming, and it's broken. It's fundamentally broken. So let's go back and model this the Clojure way. In the Clojure way, me would be a reference. Right? That's something that can change over time. 182 would be a value of me. 184 would be a different value of me. So we have separation of reference and values. Nachos would now be a pure function. Maybe a function that doesn't actually change anything. It takes an old state of me, immutable, and returns a new state of me, immutable. And then, separate from the calculation part, there's a separate thing that governs the state transition that I'm going to call a succession function. And I'll just show you what this looks like in code. I'm going to define a protocol called nachos. I'm going to define a record person that has, I actually put a name in here as well as pounds, just so I can keep track of who. And then this whole part is purely functional. Right? We have a person record that represents me at 182 pounds, and then later we're going to have another person record that represents me at 184 pounds. And the update semantics are managed entirely separate from the calculation. This is probably the single most game-changing example of simplicity in Clojure, is that you manage calculation in one place and you manage update semantics orthogonally somewhere else. One of the things that this immediately gives you, the @ sign says, give me the current value of some reference type, is I can keep track of multiple point-in-time values. Well, not to put too fine a point on it, this changes everything. People, you may have heard of the phrase incidental complexity. I'm going to sort of subset that to incidental temporal reasoning. When I'm looking at a program, I have to reason about what has happened yet. The only reason I would have to worry about what has happened yet is because something could change. If you go back and look at this previous slide, though, an enormous subset of the job in a Clojure program is made out of immutable things that can never change. So there are all kinds of places in your program where you don't have to do temporal reasoning anymore. Immediately it falls out of that the kinds of things in your traditional programs that have to be kept single-threaded because you didn't bother to reason about the concurrency semantics, that's just gone. You don't do that in a Clojure program. Typically, you don't use locks either. Right? That succession function, swap, in the previous slide, that governs the semantics of the update. And I could use different ones. There's a handful of those, maybe 10. I could have used commute or alter. But there's a small number of verbs, let's just say 10, that replace all setter methods in OO everywhere. Now, 10 verbs versus how many setter methods are there in a large application in an OO program? Thousands. But let me put in a caveat. Those 10 verbs, they actually work better than setter methods, right? Because they have well-defined compositional semantics. They say what's going to happen when you do this for multiple threads, and they do something useful when you do it for multiple threads. This also gets rid of the whole string versus string builder versus string buffer type of problem that you run into in Java. And if this is not making sense, and you come from a Java background, one thing I would ask you to ponder when you get home tonight is, why does Java have string and string builder and string buffer? And if that idea, if splitting that into 3 like that makes sense for modeling strings, why doesn't it make sense for modeling everything? And the answer is it does make sense for modeling everything. It's kind of a crummy way to do it, right? But it does make sense to model that for everything, right? String's an immutable thing. String buffer and string builder represent building things. Clojure actually has clearly defined concepts for immutable things, things that are in the process of being built, references to immutable things. And of course, again, all of these sources of complexity in your program are combinatorial, by which I mean that you get a combinatorial explosion of problems as your program gets bigger. Right? These problems hurt you a little bit if you have a small program. They hurt you a lot when you're trying to build a big program. And object-oriented programming, as typically understood, doesn't have any answers for these problems. Right? The means of abstraction in object-oriented programming, interfaces, doesn't say anything about, I want to do something to this interface, and I want to do something to that interface, and I want to have some sort of semantics about time across those things. There's not an answer to that question at all. Now, most of us, if you haven't thought about this, you end up seeing that not as that problem. You end up seeing it as a downstream symptomatic problem, which is, I wrote my code and I could only use it from one thread. Right? Or I couldn't figure out how to sort of plug my thing into the world of MapReduce or something like that. You see it as more concrete problems, but the underlying problem is not having a model of time, not having a model of references separate from a model of values. So we've looked at 3 ideas. There are dozens of examples like this in Clojure, where something that's a single idea or 2 ideas in traditional object-oriented programming becomes 5 ideas or 10 ideas in Clojure. Now I want to talk about the benefits of that to you as a program. What's going to happen to you as a programmer when you start using Clojure? What is this simplicity going to mean? And we're going to look at concision, so shorter programs, generality, right, a program being able to do more things rather than being very specific, robustness, programs having a better chance of being right and staying right, and then finally agility, I can change my program. So let's start with concision, and I'm going to take an example here from Java. So this is from the Apache Commons, one of the various Apache Commons libraries. And it's a method called indexOfAny. And this is actually just taken from their docs. The job of indexOfAny is to find the position of some character in a string. So let's look at the last one here. I'm looking for the character Z in the string ABA. You can see Java's old school C heritage showing here. Right? The indicator for I couldn't find it is -1, which is a position that doesn't make any sense. If I'm looking for the character B or the character Y in that longer string, well, okay, B is at position 3. So this is the idea of indexOfAny, and this is the Java implementation of that. What I'm going to do is I'm going to convert this program, which is a Java program, into an idiomatic Clojure program. So the first thing I'm going to do is I'm going to drop out all the corner cases. So it turns out that when you program functionally, the corner cases tend to fall away. Second thing I'm going to do is I'm going to get rid of all the type information, because Clojure is a dynamically typed language. The third thing I'm going to do is I'm going to introduce a when clause and sort of a higher order function. Then I'm going to introduce a comprehension. So if you come from Python, you've seen comprehensions before. So a for is Clojure's comprehension form. And then I'm just going to go ahead and convert the syntax to Clojure's Lisp syntax. Now what you've done here, and now let me just read this to you. Index filter is a function of a predicate and a collection that says if you did pass me a predicate, then for every index and element in the indexed collection, when that predicate applies to that element, return the index. So I almost can read this in English. Notice, and we'll come back to this in a minute, that this is a little bit different from the original program. The original program talked about strings and characters, and it returned the first index of something. This actually returns all the indexes that match, not the first index that matches. So it's a little bit of a different program. Obviously, it's shorter, right? It's, give or take an order of magnitude shorter. And you could, we're making fun of Java here a little bit. You could achieve a similar shortening by converting the Java program to a Ruby program or a Python program. Right? There are a lot of different sources of verbosity in the Java program. So this kind of concision is not necessarily unique to Clojure. But now I want to talk about generality. So I'm going to give you a completely different example that shows you how code is more general. No, I'm just going to go back to that example. Right? If you go back to that example, the original Java version searches strings. The Clojure version searches anything that's sequential. So anything that knows how to apply sequential order can now be searched. The original Java version matched characters. Right? Does this character exist in the string? The Clojure version says match any predicate. The original Java version said return the first match. Clojure says return all the matches, but do it lazily. Right? Which isn't going to do any more work. Right? If I only have to find the first one, then a function that gives me all the matches lazily is actually more powerful. It's more general. And so now I can reuse this program to do radically different things. So this first program here says find the occurrence of H, which stands for heads, in a stream of coin flips, TTH, TH, blah, 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 blah. And that says, well, heads came up at 2, 4, 8, and 9. I'm using the exact same program that I would have used to do indexOfAny or whatever string we use. Or tell me when the Fibonacci numbers pass 1,000. Right? So grab all the Fibonacci numbers, which is infinite, by the way. Right? This returns an infinite thing. And then filter such that I want something where the number is greater than 1,000. The percent sign is an anonymous argument there. So the 17th Fibonacci number is the first Fibonacci number that passes, that's bigger than 1,000. The result of this makes programs more small in a radical way. Right? This doesn't take your 20-line method and turn it into a 5-line method. What does it do? It takes a 20-line method that you wrote to work with strings, and a 20-line method that you wrote to work with coin flips, and a 20-line method that you wrote to work with the Fibonacci numbers, and turns them into what? All of those things get turned into a 2-line method. And the result of this, if you want to have a glib comment that you can use to start fights in bars, is Clojure programs can have fewer lines of code than object-oriented programs have files. So the testing library that I use in Clojure, that I wrote, has fewer lines than the Spec library in Groovy has files. And you can find lots of examples like that. So we're talking about radical reduction in the size of your programs, and reduction that comes from a lot of different places. It's not just local reduction, it's more sort of global reductions in the size of programs. The third benefit that I want to talk about here, we've seen with the single example, right? The example became more concise, it became more general. Now I'm going to talk about robustness, which of course makes me have to use a different example. No, it doesn't. Let's go back and look at the same example we had before, except this time we're going to count up different things that were in the program. So in the left column is the Java imperative version. It's got a class, a function, 2 internal exits, 3 variables, 4 branches, a Boolean operation, and 6 function calls. The Clojure version has a function that is made of 3 nested function calls. So the important thing here is that 2 of these things, well actually 3 of these things are particularly horrible for helping you reason about programs. By far the most horrible thing is variables. Right? Variables, right? If you can solve the same problem with variables and without variables, you should solve it without variables. Why? Variables suck, they vary. Right? They have this really irritating habit of I can't reason about my program because they vary. Now, I'm not saying you don't need things that vary. Right? We already talked about I ate nachos and I varied. And we already talked about how you do that in Clojure. But I'm saying that lots of things don't need to vary. And when I'm looking for the index of, which coin flips there were, or when the Fibonacci's numbers, get bigger than 1,000, or where the character Z appears in the name Stuart Halloway, those things don't require anything to vary. But idiomatic object-oriented programs make things vary. This is bad. Also, they tend to have more branches. Why are branches bad? Does anybody here write unit tests? Right? We know branches suck, right? Because what does a branch guarantee? You just doubled your number of tests right there. So branches suck. And of course, internal exit points are really just a form of branch, so we could roll them together. And the result of all this is that programs are easier to make work the first time, easier to look at and see if they work. And this leads to more robust programs. Now, the last thing I want to say from the benefits perspective is agility. Clojure programs are easier to modify and use over time than other programs. And the argument I'm going to make here is that I've already made the argument. Right? If I wanted to have 3 things in my programming language that would make it agile, I would choose concision, generality, and robustness. Right? If I could move from a programming language that had less of that to a programming language that had more of that, what would happen to my programs? They would get shorter, they would do more in their shortness, and they would be more likely to work. That has an excellent chance of being agile. The generality, sometimes the agility falls out for free. Right? Your stakeholder comes up and says, I now want the program to do this. And you're like, it actually already does that. What should I say? What should I say? Oh, that's going to take 6 story cards and about 2 weeks, and then you're outside on your front porch sipping margaritas or whatever. Having said all this, this whole idea suffers for want of a brand name, or maybe want of several brand names. One of the problems is, of course, that simplicity means there's going to be more things, not less. So Clojure probably needs dozens of brand names. One of the brand names Clojure already has is it's a concurrency language. Another brand name it already has is it's Lisp. I'm going to offer a different brand name to stick on it that I'm going to call plain immutable collection objects, just to play off of POJOs and other names people have used before. So in Clojure, your objects are plain. You don't make new classes typically to represent new information. You just use maps. They're immutable. They don't vary. They don't change. And they act as collections, which means when you make them, there's already an extant library for manipulating them. Right? Every time an object-oriented programmer creates a new class or interface, they have now protected data from algorithms. Let me say that again. If you're an object-oriented programmer, every time you make a new interface or a new class, you have now protected data from algorithms. Because you just made a new interface. How many algorithms are there out there that consume your interface? 0. Right? It's a great idea if you want to make work for people in the future or guarantee your future employment. It's not very good design. On the other hand, if you were able to actually get stuff done with plain immutable collection objects, that would be pretty great because you write stuff and the collections library just does the work for you. Everything in Clojure is represented as plain immutable collection objects. Files, XML, JSON, web sessions, web configuration, metrics, logs, databases. Everything looks like lists, sets, maps, and so forth. And I'll just show one example. This is a program I challenged myself to write. So I want to go on Rotten Tomatoes and find which actors are in more than one movie currently topping the box office charts. Well, first off, as a Clojure programmer, I'm immediately going to make the program slightly more general. So rather than saying give me the actors that are in more than one movie, I'm going to say give me the actors and how many movies they're in, sorted, with the ones that are highest first. Because if I have that program, it's going to be more generally useful, and I can obviously get this answer out of it. And so to write that program, I'd have to do the following steps. Figure out what the JSON endpoint is at Rotten Tomatoes, download it, parse the JSON, walk the movies, accumulate out the cast objects from the movies, pull out the actor names from that, get the frequencies with which the actors appear, and then sort them by highest frequency. There's the pseudocode in English. There's the program in Clojure. Notice that it has a one-to-one relationship with the pseudocode, doing exactly the same things. The minus arrow there, that's called thread last. That says take each operation and thread it as the last argument to the next one. So it's a function that rewrites programs. If you want to go back to everything works the same way. It's a function whose first argument is how am I going to rewrite this program? And then it's a list of programs that get rewritten into take the box office URI, pass it to Slurp, pass that to read JSON, pull out the movies, map concatenating the abridged cast, map the name, grab the frequencies, sort by the composition of the negative sign and second. Right, the second thing in the frequencies map is going to be how many times they appeared. The negative sign is going to reverse the sort so that the artist who is in the most movies appear first. And when I ran this last year, Shiloh Fernandez and a bunch of others were tied, including the incredibly handsome Michael Shannon. Nachos. So this idea of programming with plain collections just continues and continues. You use the exact same programming model to do big data. So there's a library in Clojure called Pigpen, which takes idiomatic Clojure programs that use map and filter and Clojure collection APIs and compiles them into Hadoop programs. So you literally take the same program you would have written to add 4 numbers, and then you put the pig prefix in front of it, and then Pigpen runs it in Hadoop for you. That's pretty powerful. One more example of that power. I'm going to go back to this me and my nachos. Imagine we applied this idea of me and my nachos to database programming. Well, what would that look like? Well, the database program would be a connection to a database. The DB, the values would be at time t1 and at time t2, the database had different values. The update semantics we would want, because we're old school about this, is we want ACID. Right? This base stuff is for making programs harder to reason about, so not interested. I want ACID semantics, and I want transact to be a pure function. Well, this is how Datomic works. Right? Datomic is a database written in Clojure. It's a commercial product. I work on it. So caveat, 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 caveat. And it presents the programming model of Clojure in an ACID database. And the thing that I want to call out here, and there's a ton of things I could say, but that in a Datomic program, the connection and the database are two different things. Right? In a traditional SQL database, you want to transact, you send data to a connection. You want to query, you go to the connection and say, give me information. In Datomic, you send your transactions to the connection, but your queries are against the database. The database is extracted from the connection. It's an immutable value that is local to your process. So queries run locally in your address space. They don't run on a server. This means that for certain small jobs, that queries can run 1,000 times faster. It also means that the caching layer disappears from your architecture. Because the whole point of like memcached and stuff like that in your system is, oh, the information is too far away. I need to get it really fast because I want to draw the latest status page really quickly. So I make all that work you do just is gone. You just ask the database. You can pound on it all you want because you're talking to something that's in memory in your own process. So how do you make something like Clojure? Well, you need to have a design. Right? You need to have a specification about how you're going to make something subject to goals to meet constraints. And so I'm going to throw out, retrospectively, a candidate goal for Clojure. Clojure's goal is to give skilled developers superpowers to build business software systems. And having written this 20 minutes ago, I already don't like it. Let's say solve hard software problems rather than build business software systems. I don't really care if it's for a business or whoever it's for. Right? So solve hard problems in software. Well, an important part of that goal is superpowers. And I'm not going to say more about that. I'm going to refer you to the previous 30 minutes of the talk. Right? The superpowers are concision and robustness and generality. But I do want to talk about how are we going to get skilled developers to solve hard problems using Clojure? Because that's about packaging. That's about what you make and how you release it. So this is going to impose some constraints. We're going to need to be open source. I'm just going to go ahead and presume that. And I think this is a safe environment where I'm not going to get yelled at for that. We're going to need to be open source. Developers are not going to flock to the banner of a closed source language in 2014. It needs to be open source. It needs to target established platforms. That's a little bit more subtle. Right? There are shops that say, we can do anything as long as it's Java. OK. Right? I'm Clojure. I got a jar for you. Right? That's important. For viability, Clojure needs to perform as well as the things that it might replace. And it needs to be stable. So these are constraints that are going to be applied. Well, let's talk about each one of those. Open source. Open source, of course, if you're going to apply the idea of simplicity to it, it's a multifaceted decision. There are dozens of sub-decisions about open source. And I'm interested about talking about this particular concept with people in this crowd. So I will be around after the talk if you want to talk about details of stuff that I'm about to say. We're licensed under the EPL. There is a contributor agreement. We think that's important. Because if you don't need a contributor agreement, it doesn't hurt you that we have one. If you do need a contributor agreement to protect IP, if you're a big Fortune 500 company that you care about, then you care. We want this to be usable by devs. Now, the contributor agreement may get in the way of casual contribution. You will notice that casual contribution was not on the goal list. Right? The goal list was superpowers for devs building software to solve hard problems. So there's a trade-off there. We put artifacts in Maven Central because that's where people go. Not big fans of Maven, not big fans of Maven Central, but that's where stuff is. And the open source, this umbrella extends not just to the language, but to a batteries included set of 30 or 40 other libraries as well. Things that might surprise you. We take patches, not pull requests. No thanks, pull requests. Frankly, we would prefer to have design documents over patches. Right? We'd much rather have a wiki page saying, here's an idea for something to put in Clojure, and here's how I think it would work, here's the pros and here's the cons. And frankly, we would prefer problem statements over designs. Where does all this come from? Is there something wrong with pull requests? Not necessarily. Right? There's just different ways of looking at the world. Clojure proceeds by design, and pull requests are the very end state. Right? They're the very last thing. I thought about a problem. I had a problem in my head. I used that problem to make a good problem statement. I used that problem statement to create a design. I used that design to write some code, and then I sent you the code. Right? When somebody sends us the code, we're like, oh, no, not again. Right? We have to go do all the work again backwards to go back and get to the stuff that's interesting in order to assess the problem. Now, let's talk about some of the other constraints. I'm not going to talk about targeting established platforms. Let me just say Clojure compiles to the CLR, the JVM, and JavaScript. We consider those to be sufficiently broad to reach people. So those are important platforms. That's where Clojure can be found. What about performance? Well, this is taken from the Alioth benchmarks. And roughly what this shows is that statically typed languages and Lisp dialects are faster than dynamically typed languages. That's a totally unfair generalization, but I don't have time to go into all the details. But the big thing is that if you're using Java or C# on your project, you don't have to rule out Clojure from a performance perspective. The other thing I want to say is that this is a logarithmic scale. So PHP here is 50 times slower than the fastest, not 2 times slower. So 50 times is that kind of order of magnitude thing that says, oh, I can't write my database in PHP. Right? I can consume a database from PHP. I can build a web app from PHP, but I can't write a database. And finally, you want to have stability. Stability is all about, frankly, stability is about being a stick in the mud. Right? We're already stick in the mud, right? We require a contributor agreement, and we don't accept pull requests. So if that's not enough to guarantee that nobody shows up and contributes anything that'll make it unstable, we also say no to almost everything people suggest. Right? In fact, we would probably be just as well off to take a 20-sided die and roll it every time a contribution comes in. And if you don't roll a 20, just reject it out of hand. Right? The result of that is that the programming language Clojure has been remarkably stable. I wrote the book Programming Clojure. It was released in 2009. And I have maintained the book Programming Clojure over what will soon be 8 releases since then. The 1.1 release required no change. The 1.2 release required no change. The 1.3 release of Clojure made a couple of semantic changes that could be significant for some programs. They were not significant for the book programs. The changes for me were small. The 1.4 release, no change. The 1.5 release, no change. The 1.6 release, no change. The 1.7 release, when it comes out, probably early next year or later this year, no change. This is a huge deal for people who are building professional software. And it's tied directly to the ways in which we build open source differently. Right? We're very slow. We are perfectly happy for an idea to sit in Jira for 2 years if we haven't thought through what the right answer is for how it should be included in the language. And the result of that is people have a stable foundation on which to build. Now, having said that, one size does not fit all. The Clojure way is not the only way to build things. There are lots of other ways to build open source. And the thing that I would encourage people to do is not put everything under one umbrella. Apply the ideas of this talk and simplify. Right? The work process of building an open source library, and how you manage it, what you do, is not different than any other design challenge. It's something that needs to be designed and built out of simple parts to achieve goals. When you enumerate your goals and the simple parts that you have at hand to build them, you may come up with radically different ideas than the ones that Clojure has. Just to remind you the ideas that we've seen 3 examples of simplicity. We've seen Clojure's syntax, which eliminates all kinds of boilerplate code. We've seen protocols, which fixes the limitations of classes and interfaces. We've seen values and references, which fixes the problem of setters and sort of uncontrolled mutation about programs. And we've given that last a brand name, which is a plain immutable collection objects. And we've seen that working that way makes programs that are more concise, more general, can do more things, more robust, more likely to work and more likely to continue to work under new circumstances, and more able to change over time. That's Clojure. I work for Cognitect. We're based in Durham, just up the road. My name is Stuart Halloway. That's my handle on Twitter. I would love to engage with you in an ongoing conversation about this. Anything that we've talked about today, I'm very passionate about it. And I will be around in the hall after the talk if we don't have time for questions here. And I think I can open it for maybe 1 or 2 questions, depending on how fast you can talk. Yes?
So when I'm talking about Clojure with people like I work with, one question that seems to often come up is, and you didn't talk about namespacing and how that's sort of decomplected from class names and that kind of thing, but sort of large-scale organization, how do I know where to go to extend a program or change a program or put that new function, that kind of thing?
So the question is, how do I know? Where to extend things as programs get large? Right. And a bigger question really is, I'm scared of what's going to happen when programs get large. Yeah. Right. So I've already made some arguments that that traditional OO style introduces combinatorial complexity as programs get large that Clojure gets rid of. There's no doubt that you need to document and enforce boundaries in your system so that the decisions you make over here don't affect the decisions that you make over there. Clojure has a modularity system. It's got namespaces. Those namespaces correspond to Java package. Obviously, that's not a hard wall, right? There's nothing that says this package can't, call that package. It is definitely up to you to be a sophisticated adult about doing that stuff. If you are working in a traditional Java shop where people are used to using interfaces, I think that's a great way, right? Clojure makes interfaces. Clojure can implement interfaces. So the way you make boundaries in your system is not radically different than the way you do now. People who are involved with the microservices movement, Clojure is very well aligned with that kind of thinking, right? That's a great way to introduce boundaries in your system. And I actually don't think those concerns really change very much. I do think that people are used to having support in IDEs for doing that if they're on the enterprise side, so that's a place where things get interesting. Clojure's IDE support has taken light year steps forward in the last couple of years. There's a terrific support in Eclipse. There's a new thing called Cursive in IntelliJ IDEA, which is really great. And then there are Clojure-specific IDEs, so there's things like Light Table. So there does start to be more tooling for managing projects when they get large. That was a long question, so we're done. My name is Stuart Halloway. Come see me after. Thank you.